This next session and the one after lunch will be on, well, a series of talks on lattice QCD. Our first speaker of this session is Nilmani Mathur from TIFR. He'll be speaking on computation of angular momentum of the proton using lattice QCD.
Yeah. I'm audible. Yeah. Okay. So I will be talking about the computation of angular momentum of proton using lattice QCD. So let me first give a disclaimer that I haven't worked in this area in last 20 years. So I will be reporting results from other groups. Why I'm giving this talk? Because this is an important area, and when I found out that there is no talk on the angular momentum on the lattice, then I volunteered. And because this is particularly good for our young students and postdocs, because we are also joining EIC. So that's the reason I will be giving this talk. All right. So this is first the punchline. This from the lattice, these are the results obtained in recent years. So these left side is from the QCD group, the cafe is here. Right side is from ETMC. So these are two discretization. So these side is from the Wallach action, and this side is from the twisted mass Wilson fermion action. So you can see that the gluon they found that gluon contribution, the gluon angular momentum is almost half of the proton spin. And then they also got the flavor decomposition and various for various flavors, and quark orbital angular momentum was calculated by subtracting the total from the other twos. And not direct calculation, the quark orbital angular momentum, but taking out from the other side. From ETMC, more or less, they got the similar conclusion that quarks supply about 57% and gluon supply is about 40% total spin. So these are the result. And there are error bars still, particularly for delta G, and I will talk about that. So these things, we hope that over the years this will improve, and we will have a good control on these, and Lattice can say a fantastic result about all these observables. Okay, now since this is the first Lattice talk, I will introduce in one slide what we do in space-time lattices. So we know that this is a Lagrangian for QCD, and if you want to calculate some observables in path integration formulation, so we do this way. And let's say we want to calculate some two-point correlation function, the two-point correlation function for proton. So it will turn out, it looks like this, but unfortunately we are not able to calculate these analytically. So that's why we go to lattice. So lattice, we put the quarks and gluons on the lattice and lattice side and as a link, and then we discretize our QCD action. And discretization can happen in different ways, depending on how good is the discretization. And then we calculate again. We want to calculate the some observables. The observables here. The problem earlier was that we were not able to do how to do this integration, but now this integration will be done by the stochastic Monte Carlo methods, and of course that's why numerically there will be some numerical error associated with all lattice calculation. So again, we can calculate the two-point function. So let's say the two-point function in this case we will be able to calculate because we know what's the propagator here. So earlier we didn't know analytically what's the propagator here. But we know on the lattice the propagator can be calculated, and through that the two-point function can be calculated, and the any point function in fact can be calculated depending on the errors. And the two-point function, we know that at long time it will decay exponentially with the states of the system, that excitation that you want to calculate, and it from there one can extract the observables basically. And once remember that we are using a particular space-time lattice, so you have to go to the physical results. So physical result means what? Physical results means we have input, what the input parameter here, the quark mass and coupling. So those need to be go to the continuum, And that's why first we calculating different quark masses, and then we go to the we do the chiral extrapolation to go to the physical result, and then we do the continuum extrapolation, and then finite volume extrapolation. So all these extrapolation need to be done in all lattice calculation. That's why lattice calculation takes so long time to get a good result. All right, so with that introduction, I will go to now the angular momentum calculation. All right, so okay, let's revise what's the workflow in lattice QCD. So workflow in lattice QCD is that using Monte Carlo methods, we generate a set of gauge configurations that representing the QCD dynamics on Euclidean spacetime lattices with varying quark masses, varying lattice sizes, and varying lattice spacing. So after that, we compute the Euclidean correlation functions corresponding to desired observable that we want to calculate energy state or angular momentum. So those need to be those correlation functions need to be calculated, and then we analyze the results, analyze the correlation function, and finally take the chiral, continuum, finite volume limits, and also you need the renormalization to get the physical result. So how it works for angular momentum? Yeah, so angular momentum, so we need to calculate the angular momentum that are a goal. So we need appropriate operators that can give the correlation function corresponding to the angular momentum. So we need to find out the appropriate operators for that. So let's start with the operators for angular momentum and the spins and rules. We know that in Belinfante formalism, the energy momentum tensor operator can be written down in a traceless and trace part. And traceless part, there are quark part, and there is a gluon part. And quark operator, you can write down the d mu nu. So this is well known for a long time. And the angular momentum density operator, you can write down this way, the M operator. And if you plug in these to that, you will be able to derive this angular momentum operator like this. The Ji basically is the density, the integration of the density, and Jg is similarly, you can figure it out. Some calculation it can be done easily. Okay, so the angular momentum operator that I was talking, that JQ is basically you can write down this way. So there's a two part. These are gauge invariant part. This part is corresponding to quarks helicity, and this part the orbital angular momentum. So these each part are basically you will be able to calculate on the lattice because these are the gauge invariant. So this is the famous G sum rule. These sum rule is frame independent. And these are the spin half. You can write down quark helicity, quark orbital angular momentum, and total angular momentum. And each term that I was telling gauge invariant and can be measured experimentally. As Yoshitaka was telling that there is another one. In fact, that is the first one. So that's the infinite momentum frame decomposition by Jaffe and Monod. That JP can be written down as quark spin, quark helicity, quark orbital angular momentum, and gluon orbital angular momentum. But unfortunately, all these are is defined in the light cone gauge, which lattice cannot access. And these are not gauge invariant, that he was also telling that. But nonetheless, the experimentally corresponding observable can be calculated. And the task is how to match this thing with the lattice. Can we calculate this thing so that the experimental number can be interpreted? That what is the if the quantity is gauge invariant, not gauge invariant, still we are measuring it. Remember that these decompositions are not unique. There are many ways actually, and each can have their own legitimate meanings about it. All right, so let's go back to the this operator T mu nu. So T mu nu can be decomposed in Lorentz invariant way. So many of you know the energy moment, these gravitational form factors. So these are the gravitational form factors of those, the T1, T2, D, and C. There are 4 of those, and in fact, the T1 basically at 0 momentum that can give the 0 q square that can give the momentum fraction. T2 is the anomalous gravitomagnetic moment. If you remember the electromagnetic case, this is like the magnetic moment case, anomalous magnetic moment. That's why It can be shown that the T1, the T2 for gluon, quarks per gluon can go to 0 using equivalence principle. So Lattice can also verify that. And the other thing is pressure and then the trace anomaly. These are 4 terms. And for angular momentum cases, so T1, T2 are necessary to calculate, and we will be able to do that on the lattice. And over the year, the precise result has been coming out on that. All right. Easily one can formulate some sum rule that q square equal to 0. Basically, Jg is T1 plus T2, and x at q square equal to 0 basically T1. So that's a momentum fraction. And some rule are that everything has to be 1. So that's T1 plus quarks plus gluon T1 should be 1. And if you sum up the q plus g for angular momentum, so that is half. And if you just plug these things all together, you will get another sum rule that T2 plus T2q plus T2g is 0. So basically that's also can be shown from the equivalent principle also. And Lattice can verify these things is in fact 0. So what is our task? Task is to calculate this form factor in T1 and T2, different q square, and then see, and then get this number Jg equal to T1 0, T2 0. So then we'll be able to get the total angular momentum from the quark part and gluon part. All right. So this is again summary. This is the angular momentum operator, angular momentum sum rule, and these are the operator that we need to track about. So operator here for spin, the operator is the axial vector, flavor singlet axial vector operator, and T mu nu has this operator. Gluon operator one can construct various ways, but this also this is one plausible operator. There are many other physical observable one can do, which is related to EIC physics, but I am not going to that. All right, so now I will show you how we calculate these things on the lattice. So before that, let me first tell you how to calculate any observable. So this is our space-time lattice, and this is lattice spacing A determine the UV cutoff, and this this length volume that determine the infrared cutoff. And so that's why we can do this calculation easily. And if we go to L infinity, A0 limit, so that we will get the continuum physics. All right. So let's want to calculate the mass of a proton. So we have to perturb the QCD vacuum with an operator which can excite the this quantum number of proton, the half plus. If you want to create a pion, you have to put the appropriate operator for pion. And then there is another part of the lattice, we put a sink, and we calculate the propagator between the source and the sink. These are, let's say, these are the propagators. These are very, very large metrics, depend on the lattice sizes. It could be 500 million by 500 million metrics, and we need to get the inversion of those. So that's why it takes a huge amount of time to get all these things. So once we have this propagator, then we will be able to calculate this physical quantity that I told you, like the energy states. And one can show trivially by using basic some quantum mechanics that if we excite a state at a space-time point and let it propagate, and at the end of the day, very large time slices, only the lowest state will be there. So you can do a trivial mathematics here. One can show that these 2-point correlation function can decay exponentially with the energies, and at the very large energies, you will get the excitation, and in the intermediate state, other excitations. Similarly, we can calculate the 3-point function. So what we need to do, again, the same thing. We have create the proton and we annihilate another area, another part of the lattice. But here we have to do this current interaction. The current will be interacting with one of the quarks, and depending on that, it can interact by itself. So there are 2 types of diagrams will come, and we have to calculate these diagram on the lattices. Similar way there we calculate 2-point functions. So here we have to calculate 3-point functions. So these are the 2 diagrams, possible diagrams there. So this is called the connected insertion, which is basically the current is coming interacting with one quarks. And this disconnected diagram, which disconnected insertion is basically these where quark loops between itself, but they are connected by gluons, of course. So in that sense, it is not disconnected, but it is an insertion. So these two, these topological things we need to calculate, and on the lattice, these turned out to be quite difficult, because as you can see that from these can be at any space-time point. So you need the propagator for each point to each point, as all point to all point, and you know that these are the million by billion or even half billion by half billion matrix, and you have to get each point to each point. This is extremely difficult, but people have found out how to do it cheaper way on that. So I will give you an example of one 3-point function. Let's imagine that we want to calculate GA. So this is some operator, and then we calculate this 3-point function. On one side, we will calculate by lattice, and we know that how these, if we calculate the 2-point function, how it will, the kinematic factors will be in before that. So these kinematic factors, if we can avoid it, then we will be able to get GA or HA, these form factors. So one can play tricks that how to avoid these things. So you can take the ratios of various various diagrams, 2-point function and 3-point function together. And what we'll do that this combined ratio, then we will get out these kinematics and some q square, various q square or q square equal to 0 limit, you will be able to get GA. So this is the tricks for any form factor calculation. So you take the calculate 3-point, 2-point function, and they take the ratios and get out the observables. And for angular momentum, the same tricks will play. And I will now describe how to do that. All right. So let's first talk about the quark spin contribution. What is the operator here? The operator is flavor singlet axial vector current. So this is a mu, flavor singlet axial vector current, gamma mu, gamma phi. So on the lattice, we need to compute the matrix element. So this is a nucleon, the source and sink, a nucleon, and we need to calculate the matrix element of this flavor singlet axial vector current. And one can show that, as I was telling, this will have two type of diagrams, connected and disconnected. The nucleon has U and D quark inside it, so this will be connected and disconnected, both of them. So current can have a psi bar gamma phi, psi bar gamma mu psi, or psi bar the gamma psi. Some gamma is a current structure. So depending on that, U and D will have both connected and disconnected. But the S quark will, and other quarks which is not the valence quark, they will have the disconnected insertion only. And so for them, as you can see, these will be only here. So S quark will be only here because they are not connected to the valence quark. So these will be difficult to calculate. And so that's why the S quark contribution to any matrix element are difficult to calculate. And it will be small, it will be noisy. All right, so this is the result that I compiled from actually the CAFE's one review earlier. These are the result for the quark spin, different, so these are the three, so one experiment and two other theoretical calculations. These are the three lattice result, and this is the delta U contribution to the quark spin, sigma, the delta D and delta S. As you can see, the two lattice results are more or less they close by, and if you go inner, so let's say the connected insertion, they are basically also similar, and sigmas are there is a half of this is a quark spin contribution, so they're lining more or less. Lattice result are coming quite good to the to each other, and also the experiment. So these are the latest result, and the flag summary they put these. So I got this from the flag 2021, and as you can see that yeah. So the below are the I think yeah, below are the lattice result. No, these are also lattice. But oh yeah, so okay, so above is the 2 plus 1 plus 1, the 3 flavor is 2 plus 1 plus 1, and this is 2 plus 1. So that's why they're separated out. But they're quite consistent, I would say, with each other, and there is good control of errors here. The main errors are coming from the delta S and also delta U, delta D disconnected insertion part, and those we hope that it will be improved. The CAFE, they found a better method to get this thing in control, and we hope that over the year this will be much more precise. All right, so next, so I think yesterday Raju asked a question, so I found something on that, and so I'm putting it here. The actual word identity that we know that there is a pseudoscalar density and there is a topological charge involved here. Cafe, in fact, they calculated these terms on the lattice, the matrix element of these on the lattice, and they found that these equation is satisfied by connected and disconnected instances separately. And there is a substantial contribution from the topological charge to the quark spin. So yeah, so that's the status at this point. Now I will go to the other part, like I told the quark's spin contribution, now the orbital angular momentum part. So there we don't calculate the orbital parts directly, but we calculate the matrix element for T mu nu first. So that will give you the total J, and that I will show you now. So that's my connection there. In fact, when I was a student, that was in last millennia, we did the first calculation on this. That's my connection to that. The quark orbital angular momentum from lattice QCD. So with Cafe and me, we calculated this thing. And so yeah. Now, what are the operators that one can construct out of that? On an Euclidean lattice, so we remember we need these form on the lattice operators in terms of these T mu nu. And for quarks, we can write down this way. So these are the derivative operators, and there are gluons are involved, so this will be noisy. Of course, this is not unique. You can do different ways derivative, but basically you have to take a derivative backward and forward and construct these operators. And then for gluon, these operators is this. And here, as you can see that there are lots of gauge field involved. These are these are written in terms of the placket. There are lots of gauge field involved, and with that, that's why these will be noisy. And our task is how to reduce the error bar for these cases. So that's important. So these operator, the form factor, we put this operator on the lattice and get the matrix element of the nucleon, then we'll get J mu nu. So again, the tricks here, they're exactly same. We calculate, this is a nucleon interpolating field. I didn't show it earlier. It's a nucleon interpolating field that it creates nucleon from the QCD vacuum. So we calculate 2-point function. We calculate the 3-point function of this T mu nu. And then we take the ratio the exactly same way that I showed you for J. We take the ratios, various type of ratios, and one can form various type ratios to get what you actually need. In fact, you can calculate T1, T2, T3, all these things separately, individually as a combination, various ways. So these are some of these ratios that one can formulate. The ratios are just 2-point to 3-point various combinations to get rid of some of the kinematics, some of the other form factors. To target a particular form factors. So it depends on what momentum you are projecting. So you have to play some analysis, play a game to get what actually you need. And so using that, one can go to different type of form factors. So these are from the QCD group for T11. Okay, so this is for T1. That's the fraction, momentum fraction. Quark momentum fraction, quarks and gluon, I think together. No, this is, yeah. So T1 at a different p square, and this is connected part, and then the disconnected part is also there. So yeah, so there are various form factors, various T1 form factors are calculated for quarks and gluon. They are more or less flat here. So these are as a function of p square. Then separately, as I was telling, you can do various ratios, and through that you can get individually or combinedly. So this is for T1 plus T2. Remember, T1 plus T2 is what we are looking for. So that's the T1 plus T2 at q square equal to 0. That what will give us the total quarks contribution to the proton spin, proton angular momentum. So these, so there are some variation here. So it is, as a function of q square, actually it is changing. And the top part is, yeah, so T1 plus T2 at various q square, they calculated and then extrapolated to q square equal to 0. So here are the result for all the result combined together. So this is for T1 quarks, T1 gluon, and then T1 plus T2 quarks gluon. And these are, remember, lattice calculation is done at various ion masses, so which correspond to different quark masses. Then we go to the chiral limit or physical limit. We go to the physical limit, so that physical limit you will get the physical result for that type of action. So that's why we need to calculate different ion masses. This is the extrapolation. And here T1, T2 all are separated out and they extrapolated to the physical limit. These are the result for T1, T2 separately, both connected and disconnected parts. Remember, these are not the physical result. First of all, we have to take the continuum limit, but even then it is not the physical result because the operator that you are using that is defined on the lattice. So you have to do the renormalization. And it can be done various ways. Yeah. Yeah, so these one brown color, so these are the disconnected for T1. You cannot see there. Yeah, and the connected for corresponding one UD. So these are where here, somewhere here. Yeah. You are talking only quark spin or so yeah. Maybe the numbers at the end of the day that will be better to see.
Okay.
There are numbers particularly rather than the plot, that numbers will be, yeah. Yeah, so as I was telling that there will be, we need to renormalize it. For example, let's say the quark spin, the fraction that need to be renormalized by quark and quark gluon part, there will be the mixing part will be there. So gluon part will have a gluon and quark gluon part. So the mixing need to take care, and these are the problem for calculating delta G particularly. You need to take care some particular scale you have to go, maybe ms bar scale, and so renormalization is an integral and important part of this calculation. Yeah, so here Raju, you may be able to see it more clearly. Okay, so let me explain this thing. So this is from the ETMC group. The total gluon contribution they got 42. Sorry, this is for X, not for the J. This is for X. The total gluon contribution is 42% and quarks contribution of 61%. And this is for the angular momentum part. The angular momentum part they obtained 38% from the gluon sector and 57% from the quark sector, and in fact there is a small 2% from the charm sector also for angular momentum. That's interesting. For quark spin part, helicity part, so the U quark part is 86%, but there is a very large D quark part, but that is negative. And S quark part is negative. All the disconnected part are negative, and D particularly is negative. So they turned out altogether is 38%. For angular, so when you subtract these from that, so you get this picture. The angular momentum is claiming that 18%. So this is comparison between Cafe's group and ETMC for the angular momentum components of LQ, JQ, and JG. So LQ is basically there, yeah, so they are compatible to each other very much, I would say, within error bar. So next one is, maybe this will be more relevant. So I started with that. The gluon part is 46% from Cafe's group, and U quark for quark spin is 85%, and that is becoming smaller when you add up with the D quark part. D quark part is basically half of that, but negative. So if you add up together, the quark angular momentum part is 13%, and I think the other group they got about 18%. So basically, that's the result so far. As you can see, there are still large error bar, particularly for delta G. and that need to be not delta G, but G total angular momentum, that need to be improved. All right, and as in previous talk we have heard that this is not the unique way. There is another way to do it, that is from the GTMD, and it is defined already in a previous talk. So this is the impact parameter, this is the transverse momentum. So this is like x cross p, and one can define the angular momentum out of that, but which one to take? So these people tell that the F14 may be the better way to take it, and that will be the Z component of the orbital angular momentum. And the lattice people have then defined this operator, which represent basically this. And there you have to take a quark bilinear. They are connected by the gauge field and two different space-time position at the same time. So this is basically is the operator, and this picture we got in last talk. So what is it basically? It is a staple. The staple is between this Z point to psi and psi bar point, and depending on how big is the staple, so eta is the staple length, v is the direction. So depending on that, like are you taking how far is the gauge link are going psi and psi bar, and it can be going in different direction also. So depending on that, we can define the angular momentum. Basically, if the eta equal to 0, so that will be the G angular momentum, and if it is infinite, and it's a time reversal, so both ways it can go. So even you average out both direction, so that will give you the orbital angular momentum. Generally, this is much larger than this. And I think in this paper they showed this is coming out because of the torque accumulated due to the final state interaction. So quarks is getting stuck, and when it's coming out, so it is getting a torque, and that's why these two angular momentum will be different. So he has calculated, this is by Engelhardt, there's two papers, and we saw this in previous talk, that there is a variation. So at one, this will be basically the G operator. Then it is going, if you go eta larger, so staple length larger, what is happening is that it's changing. So you average positive and negative side, and then you will get the angular momentum. So he calculated different pion masses, different Collins-Shopper parameters. And basically the basic point here is that there is a connection between these two, and depending on the staple length, one can go to one to other. But this is only one calculation. I mean, I think it's necessary to do the similar calculation in different ways also. He also showed that there is a way to get the twist from the twist 3 generalized pattern distribution, not from twist 2, that previous one, but twist 3 also. Basic point, okay, so here is the basic point. He calculated it and found out that this is pretty noisy. It is obvious that these operators are more complicated than the other one, and you need to smooth the gauge field maybe more, but it is actually larger. They are very larger. That's the conclusion, and it presented his talk last year. I don't see any paper yet out of that. Okay, so gluon helicity from Lattice. I talked about total gluon angular momentum, but not particularly gluon helicity. As you know that it is not gauge invariant, but how to define it? It can be, it is obtained from the PP collision. So basically one can play some games, and you can match these gluon helicity operator. You can go to the lattice. So thing is that you can calculate, you can construct an operator which can be the matrix element of that can be calculated on the lattice, and if you go to the large momentum of that, so that can be like a operator corresponding to a light cone gauge. So there is a connection between the light cone gauge numbers to the lattice calculation if you use the large momentum effective theory. The question is that whether you can calculate it for very large momentum or not. So we heard in last talk that delta G can be written down this way. There is a physical part and there is an unphysical part, and physical part has this convergence. The derivative of that can be 0, like the QED. Basically you are, if you can construct an operator for a physical, that will be fine. So that operator had been constructed, and this is the operator for delta G. In fact, it's done long time ago. And a gauge invariant, the gluon helicity operator, remember this will be a non-local form, and that can be written down this way. And as I was telling, that if you take E cross A at light cone gauge, so that can match with that. And if you can take the Lamet from these type of operator, it can match with that. So basically, through Lamet, you can construct an operator which can be accessible in the experiment. So this is the operator that we need to calculate on the lattice, the E cross A. And now how to put E and A, so that I will just tell about that. Remember that SG here is not low range invariant, is a frame dependent. So need to calculate in the rest and moving frame. So this is a complicated lattice calculation. And then the renormalization is not also easy. So this is the mu operator, the cafe, their group has put, and they use the Coulomb gauge, and the chromomagnetic field can be written down in terms of these plaquettes. And they obtained lattice result in different pion masses, and then extrapolated to the physical limit. This is their number at mu. This is the only lattice calculation actually. The delta G, they got the numbers about 50%. But the main problem is that this calculation is not complete yet, because the convergence problem, there is a convergence problem in the perturbative series in the Lamat. The main problem is that you cannot go to the very high momentum and get good correlator out of that. So systematic is not under control, and hopefully this will be under control soon. So looking forward, what are the outlook? As I discussed, the connected insertion, which is more or less systematics are within control. The further improvement requires the better ground state overlap with excited state contamination, maybe more statistics. So by that I mean you need better operator which can project the nucleon at a long time distance. So need better operator with maybe more sources and bigger lattice size that is necessary, and large number of configuration. The connected insertion then will be in very good control. The disconnected insertion, the systematics need to be improved. It is not really in control like the connected one, but it has, I mean, there are a lot of improvement happened in last 10 years. The further improvement requires the better sources. Again, the ground state overlaps need to be better, and we need more measurement, more statistics. So what do you need? The better operator setup, maybe distillation type or similar type, but nucleon distillation is very difficult. Bigger size lattices with large number of configuration. The large momentum, this is a real problem. So how to get the very large momentum of the lattice, the finite lattices. So as you know, the lattice momentum is 2 pi over LA. So either you have to go very small lattice spacing and very small lattices. You cannot go to very small lattices because then you are hitting the infrared divergence. So you have to get the big lattice, but very small lattice spacing, which is costly. But some improved method may be necessary. There are methods have been improved, but I think more improvement is necessary in the large momentum so that we can calculate, we can do the Lamat type of calculation. The gluon operators, the systematics are not within control. The improved operators are necessary, maybe multigrid type, the better smearing procedure maybe, and lattices with smaller lattice spacing, and because this helps to reduce the gluon operator, the noise. The renormalization, the systematics can be controlled. So this is, I think, under control. And I was wondering whether these can be extended to the nuclei, whether these type of calculation can be done for deuteron or helium. Of course, we want need bigger volumes and probably need new methodologies for that. Okay, so these are the conclusion. The lattice calculation can provide the first principle non-perturbative quantitative studies of various observables. And these observables are necessary to understand the non-perturbative structure of hadrons. And I showed you the lattice calculation are playing important roles in that, in studying the spin content, the emergence of mass. I think the Keppe will talk later. And then calculations of showing the substance, these calculations showing the substantial contribution to the, from the gluon angular momentum that we didn't know that earlier. So, but, and then there is a substantial part from the orbital angular momentum also, 15–18%. So in the ongoing exascale era of supercomputing, so we envisaged that the results from this calculation will be much more precise in maybe next 5–10 years. Similar to nucleon case, as I was speculating, this calculation may possibly be performed for low-lying nuclei also. And these are all important for the IC physics.
Thank you. Questions?
Yeah, nice talk. So in your earlier part of your talk, there was a graph plot of delta G. There were two dynamical quark ensembles. First is 2 plus 1 plus 1, or another is 2 plus 1. So
Delta G,
yeah.
you're talking this one or?
No, the very earlier part actually. Yeah.
Here.
Next one, the next one.
Next one, okay, yeah.
Yeah. So do we have an understanding why
The mismatch?
If we change the dynamical quark ensembles, the value of G is changed?
So this is compatible with this. This is okay. Where is the new one? New one is okay.
These are
19.
two
There is a paper.
different dynamical
Probably
ensembles.
this is the 19 paper is the there one. So this is compatible. The other these two are not. So these use Wilson. I think pure Wilson. This is Wilson twisted mass. And this is overlap, and this is also Wilson. Yeah, so there is you are telling there is a systematic between this one, or this band and this band.
Yeah, this band and this.
This band and this band.
Yeah.
But there is here there is a point already which is not inside it. This is compatible with this one. Well, these are the different discretization can keep different error, but at the end of the day they should match. That's clearly that's yeah. I mean, some systematic may be underestimated in one of the calculation.
Thank you.
Other questions? Raju?
Yeah, so I just want to ask a very naive question. So say one weren't obsessed with trying to understand everything in terms of twist-2 operator, twist-2 sort of.
Yeah.
And so then the angular momentum is just, it's a well-defined operator,
Yes.
right?
B cross K.
No, not B cross K, just a component T mu nu times x nu, right, or whatever, something, right? It's an angular momentum tensor. You can compute various components of it on the lattice. Yeah. And why have people tried to think about that as opposed to trying to fit everything within some B cross K and various kinds
the previous one is for T mu nu, no? All the other these are all T mu nu.
Right.
But you are telling whether they match each other.
No, but I'm just saying, so yeah, so your results are all for the components of T mu nu.
Yeah.
Yeah. So the other naive question is, and maybe this is not a question for you, is that, I mean, so since, the angular momentum has to do with components of T mu nu, then isn't it natural to look at observables that, I mean, it's a little disturbing to do computations which don't have relations to actual physical observables, right? So I mean,
through some limit.
What's that? Well, yeah, but the question is, we know that why wouldn't you look at things related to energy flow, for example, right? Because that's a natural.
But the problem is that the experimentalists are measuring that, and that is not gauge invariant quantity in terms of the delta G. That is defined. That is in the light cone.
I don't care about delta G. I'm just saying that I want to, just compute something in a lattice that can be connected to an experiment, right? The experiment, you could measure energy flow and maybe try to sort of reconstruct, I mean, it's non-trivial, something with angular momentum from that, and that's a thing that one should be trying to compute.
Yeah, sure.
The lattice and in theoretical calculations as well,
absolutely.
perturbative QCD. Yeah. So what's the
so you were telling that why don't you calculate, why are you subtracting it out from total G and basically this part, the x cross d, this part directly calculate. So we get right now we are getting LQ. So you have this quantity, we have this quantity, and that's why we're getting LQ.
Yeah, but why should one care about this in the first place? I mean, it's just some scheme-dependent decomposition. So,
yeah.
So, I mean, from the physics point of view, why should I care about some scheme-dependent decomposition? I mean, I just want to.
So this is gauge invariant. That's why we care. We can calculate it. But if you can give an operator, the particular operator, definitely, yeah, gauge invariant that can be calculated. This is one of them.
Sounds like it might be a good coffee break discussion.
Okay.
Any other final questions? Oh, yes.
These operators that you define, these are for helicity, right? For the quark spins, why don't you use like a sigma mu nu type commutator?
This is helicity, yeah.
Yeah, but why for the spin you cannot compute like a commutator of gamma nu kind of thing operator?
Commutator of gamma mu gamma
The
phi.
spin operator that we usually study.
Yeah, gamma mu gamma phi. That is calculated from the gamma mu gamma phi.
No, I'm telling commutator of gamma mu gamma nu, which is the spin operator. Why don't you calculate that directly on the lattice?
So this is calculated directly on the lattice with the gamma mu gamma phi operator, the GA.
No, not gamma phi. I'm telling gamma mu gamma nu, sigma mu.
Gamma mu gamma nu.
Commutator.
Sigma mu put under. That will be noisy. Yeah.
Oh.
And there will be operator mixing also will be there.
And second question is, when you show this overlap results from K-phase group, is it like dynamical or is it like a quenched overlap, meaning the operators are
The
overlapped?
quenched overlap.
Okay.
Yeah.
Okay, let's thank Nilmani again.